Hi, let's now discuss the harmonic oscillator problem. Our aim is to find the eigenvalues and eigenkets for the harmonic oscillator Hamiltonian. The simple harmonic oscillator is one of the most important problems in quantum mechanics. It's a problem that can be completely solved, and it illustrates many of the basic concepts and methods of quantum mechanics. One of the things that makes the harmonic oscillator problem important is that any potential well can be approximated by a simple harmonic oscillator. We know that the simple harmonic oscillator potential has the form. Let's write V of x equal to half k x minus x0 squared, where x0 is the minimum of the potential, or it's the equilibrium position. Now, if we take any potential V of x, we can expand it about the minimum of the potential. We can write this as V of x equal to V of x0 plus x minus x0. Okay, where x0 is the point where the potential is minimum. Now we can make a Taylor expansion about x0. This would be V of x0 plus V prime of x0 multiplied by x minus x0. Okay, and the next term would be V double prime of x0 multiplied by x minus x0 square divided by 2 factorial plus etc. Here V prime of x0 means the derivative of V of x at x equal to x0. Okay, so this term actually means the derivative of V of x at x equal to x0, evaluated at x equal to x0. Similarly, V double prime means the second derivative evaluated at x equal to x0. Now, if we look at the first term, it's a constant. Now, we know that adding a constant to a potential does not change the physics. For example, in classical mechanics, suppose we have a potential V of x. The force is given by minus dV by dx. Okay, so adding a constant to this potential does not change the force acting on the system, so it does not affect the dynamics of the system. Okay, so V of x and V of x plus a constant gives exactly the same dynamics for a physical system. All right, so this constant can be dropped, and this is the first derivative of the potential evaluated at x equal to x0. But we said that x0 is a minimum. If x0 is a minimum of the potential, then the first derivative of the potential at x equal to x0 will vanish. So this term is 0. All right. So the first non-zero term or first relevant term in this expansion is v double prime of x0, which is a constant. All right. And then x minus x0 whole square. All right. So you can, so there's a divided by 2. So it's half v double prime of x0 x minus x0 whole square. We see that this is exactly of the form of the harmonic oscillator potential, half k multiplied by x minus x0 whole squared. Okay. So for small x minus x0, we can approximate any potential by the harmonic oscillator potential. It can be used to describe phenomena from molecular vibrations to nuclear structure. The harmonic oscillator problem is also an important starting point for much of quantum field theory. So the techniques that we use when we solve the harmonic oscillator problem will be useful in quantum field theory. There are different ways to solve the harmonic oscillator problem. We shall start with Dirac's operator method. In this method, we shall be able to obtain the energy eigenkets and energy eigenvalues without actually solving the Schrödinger equation. We assume that the basic Hamiltonian for the harmonic oscillator problem has the same form as the classical Hamiltonian. And classical Hamiltonian has this form, h is equal to p square divided by 2m, which is the kinetic energy in terms of the momentum, plus the potential. For the harmonic oscillator, the potential is half kx square, also written as half m omega square x square. Okay, so we can write the classical Hamiltonian as p square divided by 2m, p square divided by 2m plus half m omega square x square. Now we assume that the quantum mechanical Hamiltonian also has the same form. The only thing is that in the quantum mechanical Hamiltonian, h is an operator, p is an operator, and x is also an operator. And of course, these are all Hermitian operators. And omega here is called the angular frequency. It's the angular frequency of the classical oscillator. It's related to a spring constant k by the equation omega is equal to square root of k divided by m. Now we have the harmonic oscillator Hamiltonian. h is equal to p squared divided by 2m plus half m omega squared x squared. In the Dirac method, the first step from here is to try to factorize this Hamiltonian. By factorizing, we mean that we'll try to write the Hamiltonian in the form v dagger v, where v is some operator and v dagger is its Hermitian conjugate. If we succeed in writing the Hamiltonian in this form, the solution becomes quite easy. Such factorization leads to a great deal of simplification in our calculations. So let's see if this Hamiltonian, if the harmonic oscillator Hamiltonian can be factorized. We know that the Hamiltonian has the units of energy. Now it is convenient to work with dimensionless quantities, and we can make this expression dimensionless by dividing throughout by h bar omega, because h bar omega has the units of energy. Dividing this expression by h bar omega on both sides, we get h divided by h bar omega is equal to p square divided by 2mh bar omega plus m omega square x square divided by 2h bar omega. Now, one of the omega in the numerator here can be cancelled with the omega in the denominator, and we can write h divided by h bar omega is equal to p square divided by 2mh bar omega plus m omega x square divided by 2h bar. Now we have h divided by h bar omega. We see that this m omega divided by 2h bar can be pulled out, and then we'll be left with an x square. So let's pull out in this expression, let's pull out m omega divided by 2h bar, and let's write this first. So we have got x square plus, and here we have got p square divided by 2mh bar omega, and we have pulled out m omega divided by 2h bar. So we have to divide this term by m omega by 2h bar, or multiply this by 2h bar divided by m omega. And we see that the h bar gets cancelled, the 2 gets cancelled, and we have got the second term as p square divided by m square omega square. Now we have succeeded in writing h divided by h bar omega as a factor times a sum of squares. Each term in this bracket is a square. All right, so we have written it as a factor times the sum of squares. So we are now trying to factorize this expression, which is a factor times a sum of squares. And now we know that if we have the sum of squares of two real numbers, a square plus b square, we can factorize it over the complex numbers as a minus ib multiplied by a plus ib. This can be written as, if this is z star. So if you have something like a square plus b square, a sum of squares of real numbers, you can write it as z star z. Okay. We can check this easily, just multiply. Right? First you take the first term and multiply with the first term, and then we get a square, and the first term from here with the second term in here, so that would be plus iab, right? And then we carry out this multiplication, which is minus iba, and then minus I multiplied by plus I is 1, so plus b square. So we can write this as a square plus I multiplied by ab minus ba plus b square. We know that for real numbers, or generally for numbers, ab minus ba is 0. Numbers commute. So this term is 0, and we get a square plus b square. So a factorization of this form is possible because a and b commute. Now the factorization of a sum of squares of operators as we have here may not be so simple, because if we have something like xp minus px, we cannot simply put this equal to 0. Right? So we have to be a little bit more careful when we are dealing with the sum of squares of operators. But we can still try a factorization of this form and see where it takes us. So we have a square plus b square is equal to a minus ib multiplied by a plus ib, if a and b are real numbers. The expression we need to factorize is this, and in here we have a sum of squares. Here it's not the sum of squares of numbers, it's a sum of squares of operators. So we can write this as x square plus p divided by m omega whole square. Right? Now this has the same form, a square plus b square. So we can try to factorize this as x minus ip divided by m omega multiplied by x plus ip divided by m omega. We also have an m omega divided by 2 h bar here, which we can distribute it equally to these two terms. So we can write the factorization as, or we can try the factorization, square root of m omega divided by 2 h bar x minus ip divided by m omega multiplied by square root of m omega divided by 2 h bar x plus ip divided by m omega. Right? So we are just trying this factorization. We are not sure that this is going to work because x and p are operators. Now let's name the operators appearing here. This operator we shall call as A. We shall define operator A is equal to square root of m omega divided by 2 h bar x plus ip divided by m omega. Now we see that the operator that appears here is actually a Hermitian conjugate of this thing, right? Because x and p are Hermitian operators. So if you take a Hermitian conjugate of this expression, we actually get this first expression, right? Because m omega divided by 2 h bar does not change when you take a Hermitian conjugate. X, p, m omega, none of this change. The only change is that I will go to minus I. Okay. So if this is defined as A, then the first term here is actually A dagger. So let's call these operators. A is equal to square root of m omega divided by 2 h bar x plus ip divided by m omega, and then A dagger will be square root of m omega divided by 2 h bar x minus ip divided by m omega. So clearly A and A dagger are not Hermitian operators. They are Hermitian conjugates of each other. These operators have also a name. This operator is called the annihilation operator, and this A dagger is called the creation operator. It's also called as the lowering operator, and this A dagger is called the raising operator. We shall explain these names later on. So what we have done here is that we have attempted a factorization of h divided by h bar omega as this term multiplied by, that is square root of m omega divided by 2 h bar x minus ip by m omega multiplied by square root of m omega divided by 2 h bar x plus ip divided by m omega. Okay, and we called this operator as A, and then this is A dagger. Right? We said that the names, these are named as creation and annihilation operators, but we shall soon see the justification for naming them so. Let's first check if this factorization actually works. That is, now we need to check whether h divided by h bar omega is actually equal to A dagger A. So let us find A dagger multiplied by A and see if it gives h divided by h bar omega. So this is A dagger from our previous slide, and this is the operator A. Let's multiply these operators. Now square root of m omega divided by 2 h bar multiplied by square root of m omega by 2 h bar is m omega divided by 2 h bar, which we write here. Now what we need to do is we have to take each term in this bracket and multiply it with each term in this one. Okay, so the first term would be x multiplied by x, okay, that is x square. The second term would be x multiplied by ip divided by m omega, which we write as I divided by m omega multiplied by xp. I, m, omega, these are all not operators, so we can pull them out. All right, these are numbers, and the numbers commute with operators, so we can write this multiplication x multiplied by ip divided by m omega as I divided by m omega multiplied by xp. Remember that this order cannot be changed because these are operators. Okay. Now the next term would be the multiplication of the second term in here with the first term here, which is again minus I divided by m omega multiplied by px. Okay, so that's the term here, minus I divided by m omega px, and the final term is this multiplication. All right. Now this is p square divided by m square omega square, because minus I multiplied by plus I is 1, and the rest of it is p square divided by m square omega square. Okay, let's just rearrange the terms here. We have m omega divided by 2 h bar x square plus p square divided by m square omega square. So we write that first, x square plus p square divided by m square omega square. Now the term we have left out is this thing, I divided by m omega xp minus I divided by m omega px. So we see that this term is I divided by m omega multiplied by xp minus px. And xp minus px is the commutator of x and p. So this is the commutator of x and p. All right. And we know that the commutator of x and p is IH bar. Actually, it's IH bar multiplied by the identity operator. It's always understood that there's an identity operator here, so we don't have to write it always. That's how this term gives us I divided by m omega multiplied by IH bar multiplied by the identity operator. Okay, we shall drop the identity operator hereafter. The important thing is that we see that this term is not equal to 0. This is not equal to 0. Okay, whereas in the case of real numbers, sum of squares of real numbers, we had something like ab minus ba, which we could equate to 0. But here this is not 0 because x and p are incompatible observables. These are non-commuting observables. So this gives a non-zero contribution, which is I divided by m omega IH bar. Okay. Now let's separate these terms. The first term here is m omega divided by 2h bar multiplied by x square plus p square divided by m square omega square. All right, let's write this term together first. And then the next term is we have an m omega divided by 2h bar outside. So m omega divided by 2h bar multiplied by I by m omega multiplied by IH bar. Okay. We see that the m omega here cancel. H bar also cancels. I multiplied by I is minus 1. So this gives us minus 1 by 2. So we see that A dagger A is actually m omega divided by 2 h bar x square plus p square divided by m square omega square minus half. Now we remember that this is the term that we needed. This is h divided by h bar omega. So what we find is that A dagger A is equal to the Hamiltonian divided by h bar omega minus half. We attempted to factorize h divided by h bar omega as A dagger A, but we see that it's not A dagger A exactly, it's A dagger A plus half. Right from here, we see that h divided by h bar omega can be written as A dagger A plus half. We have found that A dagger A is equal to h divided by h bar omega minus half. This means that h divided by h bar omega is equal to A dagger A plus half. So the factorization is not perfect. It did not work exactly as we expected. What we wanted was h divided by h bar omega is equal to A dagger A. But it is A dagger A plus a constant, plus a positive constant half. But this factorization is good enough for our purposes because it's easy to deal with constants. So from here we have h is equal to, right, the Hamiltonian can now be written as h bar omega multiplied by A dagger A plus half. Right? So this is the form of the Hamiltonian that we can work with. We have written the Hamiltonian as h is equal to h bar omega multiplied by A dagger A plus half. Now we shall call this A dagger A as n. Let's define n is equal to A dagger A. This operator is called the number operator, and soon we shall see why this is called the number operator. We have some interesting names here. We said that A is called the annihilation operator or the lowering operator. Okay, and we said that A dagger is called the creation operator or the raising operator. All right. And finally, we have n called as the number operator. And soon we shall see why these operators have these interesting names. We started our discussion with the harmonic oscillator Hamiltonian h is equal to p squared divided by 2m plus half m omega squared x squared. This Hamiltonian is written in terms of the position operator and the momentum operator. The properties of the position and momentum operators are determined by the fundamental commutation relations satisfied by them. Especially we had the commutator of x and p is equal to IH bar. Then we defined two new operators which are specific combinations of x and p. We had A and A dagger. And now we wrote the Hamiltonian in terms of A and A dagger instead of in terms of x and p. And the Hamiltonian had this form: h is equal to h bar omega A dagger A plus half. To understand the properties, the behavior of these operators, we need to know the commutation relation between them. So we need to find the commutator of A with A dagger. Since A and A dagger are specific combinations of X and P, we can find the commutator of A and A dagger from the commutator of X and P. So let's evaluate the commutator of A with A dagger. We just use the basic definition of A and A dagger. We know that A is defined as square root of m omega divided by 2 h bar x plus ip divided by m omega, and A dagger can be obtained by replacing the plus I here with a minus I. So that's the A dagger that we have here. Now we need to evaluate this commutator. We can use the property if you have a commutator of CA with DB, where A and B are operators and C and D are numbers, then we know that this can be written as CD multiplied by commutator of A with B. You can easily show this using the basic definition for the commutator. So the product of the constants here give us m omega divided by 2 h bar, and that's outside of the commutator. And we have to evaluate the commutator of x plus ip divided by m omega with x minus ip divided by m omega. And for this we can use this property. If you want the commutator, if you want to find the commutator of the sum of operators, say a plus b with c plus d, we know that, again, you can show using the fundamental definition of the commutator that this is equal to commutator of A with C plus commutator of A with D, and then commutator of B and C plus commutator of B and D. We just have to take all combinations and add them. All right. So here also we'll have 4 terms when we expand this commutator, but we immediately see that 2 of them are going to be 0 because this combination of commutator of x and x, this is going to be 0. Similarly, this combination is also going to be 0, commutator of p with p. The only non-zero commutators are this, the commutator of x with minus I by m omega multiplied by p, and this thing, the commutator of ip divided by m omega with x. All right. So let's write the first non-zero commutator, which is minus I divided by m omega can be pulled out. Okay. And then we have commutator of x and p. And the second non-zero commutator is I divided by m omega multiplied by commutator of p and x. Okay, that's what we have here. Now we know that the commutator of p with x is equal to minus the commutator of x with p, because the commutator is antisymmetric. So this commutator of p with x can be written as minus the commutator of x with p. And then we see that these two terms are exactly the same. Here we have got minus I by m omega, commutator of x with p. And here also we will have minus I by m omega, commutator of x with p. So we can add them up. We get twice the first term, right? So we get this as 2 divided by m omega divided by 2 h bar and minus I by m omega, commutator of x with p. We see that some of the terms cancel here, all right, and we have got minus I divided by h bar multiplied by commutator of x with p. And we know that the commutator of x with p is I h bar. So we end up with minus I divided by h bar multiplied by I h bar. H bar and h bar cancel, and minus I multiplied by plus I is just 1. So we finally obtain the commutation relation A with A dagger. The commutator of A with A dagger is 1. We shall see that some of the interesting properties or the interesting properties of A and A dagger follow from this commutation relation. We wrote the harmonic oscillator Hamiltonian as H is equal to H bar omega A dagger A plus half. Then we defined the number operator N is equal to A dagger A. And then the Hamiltonian can be written in terms of the number operator as H is equal to H bar omega N plus half. Now it is easily seen that the number operator N commutes with the Hamiltonian. We can find the commutator of n with h, which is the commutator of n with h bar omega n plus half. All right. The first term involves the commutator of n with n, which is 0, and the second term involves the commutator of n with a number, which is also 0. So clearly the commutator of n and h is equal to 0. This means that the eigenkets of n are also eigenkets of H. This is something that we have seen in the first chapter. So we can label the eigenkets of H by the eigenvalues of n. And this is exactly what we are going to do. Now, if you remember from the first chapter, we know that if two operators commute, they have a complete set of mutual eigenkets. So if n and h commute, we can find a basis in which both n and h are diagonalized. This means that there exists a basis in which the matrices representing n and h are diagonal matrices. Let's now take a look at the eigenvalue equations for the number operator and the Hamiltonian. We shall denote the eigenvalue of the number operator by small n. So then we can write the eigenvalue equation as the number operator acting on ket n is equal to n multiplied by ket n. Here we have labeled the eigenkets of the number operator by the eigenvalues themselves. That is, the eigenket corresponding to the eigenvalue small n is labeled as ket n. This is a notation that we have been using all this time. Since the number operator commutes with the Hamiltonian, the eigenkets of the number operator are also the eigenkets of the Hamiltonian. Let's now find the eigenvalue equation for the Hamiltonian. For this, let's check the effect of the Hamiltonian operator on ket n. We just substitute h is equal to h bar omega n plus half. Now we can use the eigenvalue equation because n acting on ket n is equal to n multiplied by ket n. Using this, we can write this as h bar omega n plus half multiplied by ket n. We have just used the eigenvalue equation. So we see that h acting on ket n is equal to n plus half h bar omega multiplied by ket n. We see that Hamiltonian acting on ket n gives you a number multiplied by the same state, the same ket, which means that ket n is also an eigenket of the Hamiltonian with eigenvalue n plus half h bar omega. Okay, so we can give the energy eigenvalues as En is equal to n plus half h bar omega. As we said before, we can label the eigenvalues of the Hamiltonian by the eigenvalues of the number operator, which is small n. We found the energy eigenvalues En is equal to n plus half h bar omega, where n here are the eigenvalues of the number operator. Okay, but to understand the nature of these eigenvalues, we need to understand what kind of numbers these n are. We know that these have to be real numbers because n is a Hermitian operator, but we don't know whether these are allowed to be positive, negative, or fractions, etc. So let's try to figure out what kind of numbers these n are. To understand this, we need to look a bit further into the operators a and a dagger. Let's start with the physical significance of operator a. This can be found by evaluating the commutator of the number operator with a. So let's find the commutator of n with a, which is the commutator of a dagger a with a. This can be found using the formula. The commutator of a b with c is equal to, this can be written as commutator of a comma c multiplied by b plus a multiplied by commutator of b and c. Okay, again you can prove this using the basic definition of the commutator. If you haven't done it already, please try this. So using this commutator can be written as a dagger comma a, the commutator of a dagger comma a multiplied by a plus a dagger multiplied by the commutator of a with a. This is the commutator of an operator with itself, which is 0. So we just have commutator of a dagger a multiplied by a. But we already found the relation commutator of a with a dagger is equal to 1. So the commutator of a dagger a has to be minus 1. And finally, using this, we get the commutator of n with a is equal to minus a. Or Na minus An. This is the definition of the commutator. We can write Na minus An is equal to minus a. To understand the physical significance of operator A, we need to find out how it acts on the base kets ket n. And these base kets themselves are the eigenkets of the number operator, obeying the eigenvalue equation n acting on ket n is equal to the eigenvalue n multiplied by ket n. So we can ask, what happens when the operator n acts on the state A ket n. What is this? And this will tell us what the operator A does to the base vectors. So let's first find this n acting on A ket n. We can now use the commutation relation na minus an equal to minus a, or we can write na is equal to an minus a. You just take this to the other side of the equation. So we write n acting on a ket n is equal to an minus a acting on ket n. But we already know that n acting on ket n is equal to the eigenvalue n multiplied by ket n. We can use this eigenvalue equation and we get this is equal to a multiplied by the eigenvalue n minus a acting on ket n. Now this n is a number commutes with the operator, so we can write this also as na minus a acting on ket n. Now we can pull out this a and we see that this is equal to n minus 1 multiplied by a ket n. So we started with the state a ket n and acted the operator, the number operator on it. And we see that we get exactly the same state multiplied by a number. Okay. In other words, the state a ket n is also an eigenket of operator n, but the eigenvalue is n minus 1. What we saw is that if ket n is an eigenket of the number operator with eigenvalue small n, then a ket n is also an eigenket of n, but with the eigenvalue decreased by 1. Okay. So we see that a acting on ket n is another eigenket of operator n. All right. Ket n itself is an eigenket of operator n with the eigenvalue n. All right. Then a acting on ket n is another eigenket of operator n, but with eigenvalue n minus 1. All right. So we found that n acting on a ket n is equal to eigenvalue n minus 1 multiplied by n minus 1 multiplied by a ket n. So the effect of operator a on ket n is to take it to another state with eigenvalue decreased by 1. Okay. We found that the number operator acting on a ket n is equal to n minus 1 multiplied by a ket n. Since the number operator commutes with the Hamiltonian, a ket n has to be an eigenket of the Hamiltonian also. Let's find the corresponding eigenvalue equation. We see that h acting on a ket n can be written as h bar omega n plus half acting on a ket n, because this was the expression for the Hamiltonian. Now we know that a ket n is an eigenket of the operator n with the eigenvalue n minus 1. So we can replace this operator by the corresponding eigenvalue, which is n minus 1. So this becomes h bar omega n minus 1 plus half a ket n. We can rearrange this a little bit and we can write this as h bar omega n plus half minus h bar omega multiplying a ket n. We see that the Hamiltonian acting on a ket n reproduces the same state with a number multiplying it, which means that a ket n is an eigenket of the Hamiltonian, but with eigenvalue h bar omega n plus half minus h bar omega. Now what is this h bar omega n plus half? We know that h bar omega n plus half was the eigenvalue for the Hamiltonian corresponding to the state ket n, because we had h acting on ket n equal to h bar omega n plus half multiplying ket n. All right. Now we see that when we go to the state a ket n, the eigenvalue has decreased from h bar omega n plus half to h bar omega n plus half minus h bar omega. What we see is that a ket n is an eigenstate of the Hamiltonian with unit energy, with a unit of energy h bar omega less than the state ket n. So the action of the operator a on the base ket n is to take it to a state with a lower energy. Lower by how much? Lower by an amount h bar omega. For this reason, a is referred to as the annihilation operator because it annihilates a unit of energy. Okay. It is also referred to as the lowering operator because the effect of a on ket n is to lower the energy by an amount h bar omega. Now this is the physical significance of operator a. And this is the reason why operator A is referred to as the annihilation operator or the lowering operator. In the same way, we can understand the physical significance of A dagger also. Let's start by evaluating the commutator of n with A dagger. Again, we substitute n equal to A dagger A, evaluate the commutator. Okay, here I have written only the non-zero commutator, and A with A dagger, the commutator of A with A dagger is equal to 1. So we find that the commutator of n with A dagger is equal to A dagger, or n A dagger minus A dagger n is equal to A dagger. All right, we can write this as n A dagger is equal to A dagger plus A dagger plus A dagger n. Okay. As before, let's examine the effect of A dagger on the base gets ket n. We do this by looking at the effect of the number operator on the state A dagger ket n. Again, we use the commutation relation n A dagger is equal to A dagger plus A dagger n, and we finally get n acting on A dagger n is equal to 1 plus n multiplying A dagger n, or A dagger n is also an eigenket of operator A with eigenvalue 1 plus n. That is, if ket n is an eigenket of the number operator with eigenvalue small n, then A dagger ket n is also an eigenket of operator n but with eigenvalue increased by 1. Similarly, the state A dagger ket n is also an eigenket of the Hamiltonian. We can find the corresponding eigenvalue equation just as before, and we find that H acting on A dagger ket n is equal to h bar omega n plus half plus h bar omega multiplying A dagger ket n. We see that A dagger ket n is a state with an amount of energy h bar omega more than the state ket n. Let me repeat, we find that A dagger ket n is an eigenstate of the Hamiltonian with 1 unit of energy h bar omega more than the state ket n. For this reason, A dagger is called the creation operator. It's also known as the raising operator. Together, A and A dagger are referred to as the ladder operators. Okay. We had n acting on A ket n is equal to n minus 1 multiplying A ket n. This means that A ket n is an eigenket of operator n with eigenvalue n minus 1. But earlier we said that we shall label the eigenkets of operator n or the number operator by the corresponding eigenvalues. That's why we wrote n acting on ket n is equal to eigenvalue n multiplying ket n. Here we have labeled this eigenket using the eigenvalue of operator n. This means that the eigenket corresponding to the eigenvalue n minus 1 will be labeled as ket n minus 1. So that n acting on ket n minus 1 is equal to n minus 1 multiplying ket n minus 1. We are just labeling the eigenkets using the eigenvalues. Okay. Now we have n acting on A ket n is equal to n minus 1 multiplying A ket n, and n acting on ket n minus 1 is equal to n minus 1 multiplying ket n minus 1, which means that both A ket n and ket n minus 1 are eigenkets of operator n with the same eigenvalue n minus 1. So these are the eigenkets of operator n corresponding to the same eigenvalue, which means that they are the same up to a multiplicative constant. So we can write A ket n has to be something like a multiplicative constant c multiplying ket n minus 1. Here c is some numerical constant, generally a complex number, that has to be determined from the requirement that both ket n and ket n minus 1 are normalized. So we are taking the set ket n as the set of normalized eigenkets of operator n. And then we can write the state A ket n as a multiple of one of the normalized eigenkets of operator n. So let's evaluate this numerical constant c by demanding that ket n minus 1, etc. are normalized. Okay. We found that A acting on ket n is equal to ket n minus 1 up to a numerical constant. Now let's find the inner product of this vector with itself. Alright, so the corresponding bra can be written as bra n, or the corresponding bra equation is written as bra n A dagger is equal to bra n minus 1 C star. Okay, now let's find the inner product with itself. The left hand side becomes bra n A dagger multiplying A ket n. This is the inner product of A ket n with itself. This is equal to, on the left hand side we have C star. Let me write it as bra n minus 1 C star. That's the bra, and the ket is C multiplying ket n minus 1. Here C star C equal to modulus of C square is a number which can be pulled out. So this becomes modulus of C square bra n minus 1 ket n minus 1. Now we said that this ket n minus 1 is a normalized eigenket of operator n, which means that the inner product with itself has to be equal to 1. So we have bra n A dagger A ket n is equal to modulus of C square. We have bra n A dagger A ket n is equal to modulus of C square. But the A dagger A appearing here is the number operator. So we can write this as bra n number operator ket n is equal to modulus of C square. Now we can use the eigenvalue equation n acting on ket n is equal to the eigenvalue n multiplying ket n, and then this equation becomes bra n multiplying ket n is equal to modulus of C square. This n is a number, so we can pull this out of this inner product and we get n multiplying bra n ket n is equal to modulus C square. Now we said that we have defined the ket n as the eigenkets of operator n which are normalized, which means that this is equal to 1. Okay, these are the normalized eigenkets of operator n. So this is 1, and we get n is equal to modulus C squared. This means that C can be written as square root of n, and there could be a pure phase factor of this form, e raised to I delta. But since this does not change the normalization of the state, we can choose to drop this, and we can write C is equal to square root of n. Okay, and we have finally A acting on ket n is equal to square root of n multiplying ket n minus 1. This is the relation between the state A ket n and the normalized eigenket ket n minus 1. Okay, we shall be using this in calculations. By similar arguments, we can say that A dagger acting on ket n is some numerical factor d multiplying ket n plus 1. We can find d demanding that ket n plus 1 and ket n are normalized eigenkets of operator n. So to get this, we take the inner product with itself on both sides, and from the left hand side we have bra n A dagger ket n, and on the right side we have bra n plus 1 d star d ket n plus 1, which is modulus of d squared. Now the left hand side, we see that A dagger is not immediately the number operator, but we can write this in terms of the number operator using the commutation relation. So we had commutator of A with A dagger is equal to 1, or A dagger minus A dagger A is equal to 1. We can say that A dagger is equal to 1 plus A dagger A. So we can substitute A dagger equal to 1 plus A dagger A in here, and we get bra n 1 plus A dagger A ket n is equal to modulus of d squared. Now A dagger A is the number operator with eigenvalue small n for the state ket n. So we can write this as 1 plus n multiplying ket n. Now this is a number which can be pulled out, and we can write this 1 plus n bra n ket n is equal to modulus of d square. But again, as we said, these are the normalized eigenkets of operator n. So this inner product is 1, and we get 1 plus n is equal to modulus of d square. Okay. And we can drop the phase factor as we mentioned previously, and we can write d is equal to square root of 1 plus n. So we finally have A dagger acting on ket n is equal to square root of n plus 1 multiplied by ket n plus 1. Now we have found A acting on ket n is equal to square root of n multiplied by ket n minus 1, and A dagger acting on ket n can be written as square root of n plus 1 multiplying ket n plus 1. We are going to use these relations, so you have to remember this. Now consider the equation A acting on ket n is equal to square root of n multiplying ket n minus 1. Now let's apply the annihilation operator A to both sides of this equation. So the left side becomes a square acting on ket n, and right hand side becomes a acting on square root of n multiplying ket n minus 1. Now here square root of n is a number, so it commutes with the operator, and we can write this as square root of n multiplying a acting on ket n minus 1. Now what is a acting on ket n minus 1? From here we see that a acting on ket n is square root of n multiplying ket n minus 1. So using the same relation, here instead of ket n we have ket n minus 1. So we should have square root of n minus 1 multiplying ket n minus 2. Or we can write this as square root of n into n minus 1 multiplying ket n minus 2. This is a square acting on ket n. So a square acting on ket n is square root of n into n minus 1 multiplying ket n minus 2. And a cube acting on ket n is equal to square root of n into n minus 1 into n minus 3 acting on or multiplying ket n minus 3. Now we see that if we start with an n that is a positive integer, this sequence is going to terminate. For example, let's start with the state ket n is equal to ket 2 or n equal to 2. And let's apply the annihilation operator to this state, a acting on ket 2. So this is equal to square root of 2 multiplying ket n minus 1, that would be ket 1. Let's apply the annihilation operator again. A square acting on ket 2 is equal to square root of 2 into 1 multiplying ket 0. If we do that once more, a cube acting on ket 2 would become square root of 2 into 1 into 0 multiplying ket minus 1. Let me write it like this, ket minus 1. But this state does not exist because this is 0. We are multiplying a ket here with 0, so this is the null ket, 0, or the 0 vector in the Hilbert space. Since we have a null ket here, if we keep applying this operator again, alright, the annihilation operator again, we are going to get 0 again and again because we are multiplying something with a 0. This also means that if n is a positive integer, then there is no state corresponding to n equal to minus 1. There is no state corresponding to a negative value for n because this is the last state. If I apply the annihilation operator to this state, we get 0. So by applying a continuously, we can get eigenkets with smaller and smaller n until the sequence terminates. And this happens whenever we start with a positive integer n. But this sequence will not terminate if we start with a non-integer n, say something like 2.5. In this case, the sequence is not going to terminate, which means that in that case, there would be eigenkets with a negative value of n, or eigenkets corresponding to a negative value for n. Now the question is, can the eigenvalues n be negative, or can there be states corresponding to a negative value of n? And the answer is no, n cannot be negative. This can be seen by considering the norm of the state a ket n, a acting on ket n. Let's find the inner product of this state with itself. The inner product of this state with itself would be bra n, a dagger a, ket n. Now we know that the inner product of a vector, a ket with itself, has to be greater than or equal to 0. This was the postulate of a positive definite metric. The inner product of a vector with itself has to be greater than or equal to 0. But what we have here is the number operator. So we can write this as bra n, operator n, ket n is greater than or equal to 0. Now we can use the eigenvalue equation. So this becomes bra n, eigenvalue n multiplying ket n is greater than or equal to 0. And this n can be pulled out. We can write this as n multiplying bra n ket n is greater than or equal to 0. Now this is equal to 1 because these are the normalized eigenkets of the number operator. And we finally get n has to be greater than or equal to 0, which means that n cannot be negative. This also means that n cannot be a non-integer. It has to be an integer because if we start with something like n equal to 2.5, a non-integer value, then by continuously applying the annihilation operator to this state, let's say the state ket 2.5, By continuously applying the annihilation operator to this, we can construct states corresponding to minus 1.5 or minus 0.5, etc. Okay. But we saw that if we start with n as a positive integer, then the sequence terminates at get 0 and we cannot construct states corresponding to n less than 0. Alright, if we start with n as a positive integer. So the fact that n is greater than or equal to 0 also means that n has to be a a non-negative integer. It can be 0 or it has to be positive. It has to be a non-negative integer only. In that case, this sequence of applying the annihilation operator continuously terminates at get 0 and we cannot construct states corresponding to n less than 0. Okay. So we conclude that the sequence must terminate with n equal to 0 and that the allowed values of n are non-negative integers. This is the reason why we call the operator n as the number operator. Its eigenvalues are non-negative integers. The state corresponding to n equal to 0 is denoted as get 0. This is actually the ground state because this is the state corresponding to the lowest value for n, which means that this is also the state corresponding to the lowest possible energy. We already saw that the get 0, right? Get 0 is such that the annihilation operator acting on get 0 gives a null get, which means that there is no state corresponding to a lower value for n. Note that what we have here is the null get and not the number 0. And a null vector or a null get does not represent a physical state. So what this equation means is that there is no state corresponding to a lower value of n. Alright? Now you should not confuse with this label get 0. This is not a null get. Alright? This is just the ground state. And 0 here is just the label for the state. Right? Whereas this 0 here is the null get. Okay, this is not the null get. Don't get confused by this notation. We could also write this as ground state inside the ket. Right, ket ground state. All right, and there is a physical state corresponding to this ket. So here we see that the operator A annihilates the ground state. It acts on the ground state and returns a null vector or a null ket. It annihilates the ground state. So the name annihilation operator is actually justified. We found that the energy eigenvalues are given by En is equal to n plus half h bar omega, and now we realize that n has to be a non-negative integer, which means that n is 0, 1, 2, 3, etc. N equal to 0 is the lowest possible value for n, and the corresponding energy is E0 is equal to half h bar omega. In other words, half h bar omega is the ground state energy for the harmonic oscillator, or the ground state of the harmonic oscillator has an energy half h bar omega, which also means that for a harmonic oscillator, there is no state corresponding to energy is equal to 0. This is the lowest possible energy. Half h bar omega is the lowest possible energy for a harmonic oscillator. Now we have the ground state get 0. We can obtain the excited states or the higher energy states by successively applying a dagger or the creation operator to the ground state. For this, we just have to use the relation a dagger acting on ket n is equal to square root of n plus 1 ket n plus 1, or we can write ket n plus 1 is equal to a dagger divided by square root of n plus 1 acting on ket n. So let's start with the ground state and construct the excited states now. We are going to use this relation. We saw that ket n plus 1 can be written as a dagger divided by square root of n plus 1 acting on ket n. Alright. So this means that ket 1, if you take n equal to 0, we have ket n is equal to a dagger divided by square root of 1, which is simply 1. So a dagger acting on ket 0. Okay, we can find ket 2 as a dagger divided by square root of 2. Alright, so this is a dagger divided by square root of n plus 1. Alright, so ket 2 is a dagger divided by square root of 2 acting on ket 1. Alright, but what is ket 1? Ket 1 is a dagger acting on 0. So we can write this as a dagger divided by square root of 2 multiplied by a dagger acting on ket 0. This is a dagger squared divided by square root of 2 acting on ket 0. Similarly, we can write down ket 3. Ket 3 is equal to A dagger divided by square root of 3 acting on ket 2. Okay, but we already had found ket 2, so this is A dagger divided by square root of 3. And what is ket 2? It is A dagger square divided by square root of 2 acting on ket 0. We have just used this relation. Okay, now you see that this is equal to A dagger cube divided by square root of 3 multiplied by 2 acting on ket 0. Or we can write this as square root of 3 factorial. Alright, this can be written as square root of 3 factorial. So in general, we can write ket n is equal to A dagger raised to n divided by square root of n factorial acting on ket 0. Okay. We started with the ground state ket 0 and simply applied the raising operator to generate the excited states. And in each step, the energy is increased by h bar omega, right? Because we know that A dagger ket n is a state with higher energy compared to the state ket n, and the energy is higher by an amount h bar omega. In this way, we succeeded in constructing simultaneous eigenkets of the number operator and the Hamiltonian with energy eigenvalues En is equal to n plus half h bar omega, where n can take values 0, 1, 2, 3, etc. These are the possible energies that a harmonic oscillator can have. The remarkable thing is that we obtained the eigenvalue spectrum without solving any differential equation, without solving the Schrödinger equation. Of course, we can obtain the same result by solving the Schrödinger equation also. We shall be seeing this later. But this operator method by Dirac is simpler and more elegant. You may note that the energy of the harmonic oscillator is quantized. It can take only discrete values for energy, because we had En is equal to n plus half h bar omega, where n can take values only 0, 1, 2, 3, etc. So the lowest value for energy is E0. The ground state energy is half h bar omega, corresponding to n equal to 0, whereas the first excited state energy E1 is equal to 3 by 2 h bar omega. Alright, and the second excited state energy is equal to 5 by 2 h bar omega. So the harmonic oscillator can take energy half h bar omega, 3 by 2 h bar omega, 5 by 2 h bar omega, etc. But it cannot take energies between these values. This is what we mean when we say that the harmonic oscillator energies are quantized. So any number you can think of is not a possible energy of the harmonic oscillator. All right, you can think of a number between this, but the harmonic oscillator cannot take an energy between half h bar omega and 3 by 2 h bar omega. Okay. The figure here shows the energy spectrum of the harmonic oscillator along with the potential energy curve V of x equal to half m omega square x square. So the plot here, this parabola is the plot for the potential V of x equal to half m omega square x square, and these are the energy lines. We have a non-zero ground state energy, which is E0. All right, this energy is h bar, half h bar omega. This is half h bar omega. So the lowest possible energy is half h bar omega and not 0. Okay. We also see that these energy eigenvalues are evenly spaced, all right, because we can show that E1 minus E0 is the same as E2 minus E1, which is the same as E3 minus E2, etc. You can just show that using this expression for the eigenvalue equation. I leave that as an exercise. So with that, let's conclude this session. What we have done in this session is to solve the harmonic oscillator problem in Dirac's operator method. We obtained the energy eigenvalues or the eigenvalue spectrum, and we constructed the eigenkets, and we did all this without solving a single differential equation. We saw that the energy eigenvalue spectrum is En is equal to n plus half h bar omega, where n can take only values 0, 1, 2, 3, etc. Later, we shall obtain the same result by solving the Schrödinger equation for the harmonic oscillator potential. We shall do that in a later video. Let me stop now, and I hope that you have followed the class. Thank you.